Okay, so let's start with the concepts of differential evolution. So this is why I am discussing first. There is one more reason for that, because this is only one objective function optimization problem. So we'll finish these things first, then we'll go for multiple objective functions. So one of the persons asked in, I don't remember who, but some time back, someone asked how to optimize these multiple objective functions. So that time I didn't know that these things are there in this course. I also just went through them last week only. So
Prashant had asked 2 weeks back.
Prashant, right? Okay. Okay. So do you know this person, Mr. Manohar?
Yes, sir.
Oh, so then you can ask them to join back maybe next week. Then we'll discuss.
Okay.
Yeah.
Okay. Okay, sir.
Okay, so we have differential evolution. So I'll just roughly draw the flow chart. That is, first initialize the population, then we perform mutation. So in genetic algorithm, if you remember, we did selection, so fitness calculation, selection, crossover, then mutation. This is a little different. We directly go to the mutation, then we go for recombination, then we go for selection. So this is also a very interesting approach to perform. So we'll see that. And then we go for termination, criteria checking. If it is fine, then we have the solution. If it is not, then just go back again. Oh, sorry, go back again to this thing. And here, in the middle, we have to have new generation. Okay, so let's see. So initialize the population. So let's say we have to understand this better. Let's say we have a function f of x1 and x2, and we are going to optimize this function. So whenever we initialize our solution set or our generation, first generation, we kind of want it to be uniformly spread throughout the search domain. So what is the search domain? So we have some lower limit for x1, we have some upper limit for x1, we have some lower limit for x2, and we have some upper limit for x2. So inside this uniformly distributed points are our initial generation or first generation or the initial population. So how do we get that? We as it was shown in the equation. So population will be something like x1 x. Let me write it like this: first generation or first solution, first value, and then first generation or first solution, second value, and then second solution, first value, and second solution, second value. So something like this it will be there. How do we get these things? So we get these by x I1 is equal to, let's say, x1 lower plus some random number, and this will be like we are doing a random weightage between the upper limit and the lower limit of our x1, and then same thing we will do for the x2 also. Okay, so for this for this to be still inside this range, so we are adding some random component or random weightage of this particular length to our x, the lower limit of this thing. So for the points to be remaining inside the domain, this random number should vary from 0 to 1. So in MATLAB or in R, if we are doing rand unif, or sorry, R unif, or in MATLAB it is just rand. So probably it is going to give from in MATLAB, at least it is going to give from 0 to 1, and same as r, so we can use directly these functions. So this is going to give our initial population, and we are going to represent our initial population, let's say, in this kind of a matrix. Let's Yeah, Mr. Manohar, you can ask.
Sir, can you please explain what actually that X11 and X12 or X21, X22 means? Because I'm getting confused with that key
Okay,
X11 and X12. What does they indicate actually?
okay, we will explain. Let's take an example. Let's say we have our a function which is of three variable, x1, x2, x3, and this is our we have some search domain. So sorry, x1 is lower limit is 0 to 2, x2 has a lower limit from minus 1 to 1, and x3 has a limit from let's say 1 to 4. Now let's write our initial solution or initial first generation. In the first generation, let's say I want to have so let's say in my first generation I want to have four solutions. So I will write these four solutions one by one like this, and the first solution for my first the first variable for my first solution will be written as x11. You can write a comma here if you are confused, and my second variable for my first solution will be written as 1 2. Similarly, we have this. So let's give them some value, and we'll use these values as we go on forward. So randomly generated, right? X variable 1 should be between 0 to 2, and we have to have four solutions. So let's say it is 0 1, and let's keep it integer for our simplicity, and then 1 and 2. Variable x2 has to be between minus 1 and 1, so minus 1 0 1 1. Variable 3 is 1 2 3 4. So do you understand, Mr. Manohar, that this is one solution, this is one solution, this is one solution. X1
Okay,
2,
can we say that the number of columns in this matrix is the number of variables you are using?
and correct. Yes, this is number of variables,
Okay.
and this
So in the
is
first solution, what do each variable have the values that is being displayed in that first row?
yes, yes.
Okay. Okay, sir.
So we have number of solution. So let's use this as we go forward. So this is number of solutions in one generation. So we will see in the code it is written as np. We have taken as 4, and the variables we have taken as 3. Okay, so this is our initial population. Now, how do we do mutation after initial population in this differential evolution? We have mutation. So for mutation, what we do, let's say, so we have to do mutation for all these solutions, and we will have for the, let's say we want to do mutation for this one, for 0 minus 1 and 1, this solution. Let's call this as first solution for first generation. So this was written something, I think it was written as N and G in the PPT. So to do this mutation for this thing, we need to create what is called a donor vector that was represented as V n and G plus 1. Let me V and G plus 1. So maybe let's take it as V and G plus 1. I don't remember what was the thing. So how do we create this? We go to this solution pool, and Let me use a different color. We go to this solution pool. We have already taken this one. We want the donor for this one. So we choose the other some three out of other remaining solutions in the solution pool. So fortunately, that's why I took four, because we need three. So let's take these three. So we have to create our donor. How do we create it? We take one, any of these things. So 102, I'm writing it in the column form for our simplicity. And then we multiply with some weightage that can vary between 0 to 1, or sir later showed in the code it can vary between 0 to 2 also. So it is just this donor vector, it is just a linear combination of the randomly chosen other three vectors from the solution pool. So we have 1 1 3, and then we have minus 2 1 4. So when you do choose some value of f here, you are going to get the donor vector for this particular mutation. So let's say we choose f is equal to 1 for our simplicity. So then it will be fng plus 1 will be 1 plus this will be minus 1. So minus 1, and then 0 with 0, and 2 with minus 1. So we will have 0 0 and 1. So do you understand, Mr. Manohar, how did we get this v and g plus 1?
Yes, sir. Yes.
Okay, so now that we have v and g plus 1, we have to do the same thing for so v and g plus 1 is actually we have done for the first solution, so it is v1 g plus 1. So we have to do this for the remaining. Then we will yes, you wanted to ask something.
What this capital F is? What is it called as?
It is just a weighting factor to create a linear combination between the chosen randomly chosen other three vectors. I don't think there is a significant there is a
Okay.
significance, but I don't think there is the name was shown in the PPT. I don't remember that. We'll
No,
just
name was not shown.
we'll just
Sir has just told that either we can take 0 to 1 or 0 to 2.
yeah. So let's call this weighting factor then. So
Okay.
we'll just name it something. It doesn't matter whatever we call it. Weighing factor. Let's call it weighing factor. Okay. So now we have to do this same thing for the other other three vectors also. Let's say we did that, and we got a new set of donor vectors for each. So for the first one we had 0 0 1. Okay, and let's say we did something and we got the result for we did the same thing for other things and we got the result. I'm not going to do it. I'm just going to write some random values here. 1 1 minus 1, 2 1 4, and oh no, 2 and 4 is repeated. So then 2 2 1 and 0 1 0. Let's say we did our same operation and we got the donor vectors for each of the uh, solution vectors in the solution pool. Is that clear, Mr. Manohar? How did we get these things?
Yes, sir. Yes.
Okay, so let's say we got these things. Now what we have to do is we have to do a recombination. That means we have to combine this V and G plus 1, that is the donor donor solution or donor vector, and the initial solution. So let me see if I can take this to that place. Yeah, so we have this. Yeah, so we have this thing here, and we can just write our 0 0 1 1 1 minus 1 2 2 1 0 1 0. So what we are going to do now is we are going to run a loop, and that loop will run for each solution and each variable point. So we are going to run a loop which will go to each element, like each member of the solution. Okay, so it will go something like for I equal to 1 is to 1 is to n. So like n is here, the number of solutions, and inside that, maybe let me call it j. For I equal to 1 is to 1 is to 3. So this 3 here is the number of variable. Okay, inside this loop, we are going to check. What we are going to check? We are going to create a random variable that is going to be between 0 and 1 using our random function. So let's call that P. We are going to create that, and we are going to compare that random variable with the pre-decided threshold probability, that is Cp. So if at all P is less than Cp, less than equal to Cp, or the I that we have, this I in the loop, it happens to be equal to I rand, that is a random variable between, for this particular case it is a random integer between 1 and 3. So if this is true, or this is true, or both of these is true, then we are going to uh, keep our what we say keep our donor vector value. Let's say like we are doing for the first solution and for the first variable, we go into this loop, j is equal to 1, I is equal to 1, and probability, let's say we have Cp of 0.5, and the probability that we get from this uniformly generated random variable is 0.4. So p is less than Cp. So whether we have I is equal to, in this particular case for first loop, I is equal to 1 here, but even if we have I and some other value 2 or 3, but this case is satisfied, what is going to happen is our first value will be chosen from this particular donor vector. If it is not, then it is going to chosen from the previous generation vector. So for this case it is same, so it is not going to affect much. Okay, so one thing I wanted to discuss here is, see, the way the conditions were written in the PPT. I am not sure whether they are 100% correct or not, but the way they are written, the very high probability or very high emphasis is given to the donor vector. Means mutation is given very high preference. Why that is? Let me show you using the uh, axis, using our Cartesian coordinate. So let's say my this is my Cp that I have chosen for it is on the x-axis. So the probability on the x-axis, and the origin is having the x coordinate of Cp, and let's say I is on the y coordinate. So for one loop, assume that you have a Cp of 0.5, and I that you are getting, I rand, let's say you are getting 2, this I rand. So when you are going to choose your donor vector, you are going to choose your donor vector when you have your probability less than Cp. That means this area, or you are going to have I is equal to 2. So since it is an integer, so let's say we have this area something. How do we design assign this thing? So okay, sorry. Let's say 2 has this much probability. So do you understand, Mr. Manohar, what is happening here?
Yes, yes.
So this is it is so let's say we had 1 to 3, right? So the I will be divided into three regions. So this is the region where I is equal to 1, this is the region where I is equal to 2, this is the region where I is equal to 3. So this, if this is true, doesn't matter, or if I has happened to equal to be true, this is the region where if our solution or the random value falls, we will have to choose our donor vector instead of the previous generation, right? Only in these two regions can we be allowed to choose the previous generation. So mutation is given a little bit of slight advantage over the uh, previous generation here. I just wanted to show that. So, and anyhow, so the thing is, I don't know whether it is correct to say that if we have the CP of zero point 0.5, it is sure shot that we will have 50% from the donor vector and 50% from the original vector. We will have certainly a little more from the donor side. So something this I wanted to show. Okay. So we
Yes,
do,
sir. Because
yeah.
even in the slide it is mentioned that we select the element from donor,
Hmm.
either this condition or that condition, means
Yes.
or condition is used,
Yes.
and for original element and condition is used.
Yeah. So when we use or, the probability is increasing, and we use and, it's like
Yes,
probability decreases. Yeah.
yes.
So this is the case. So using this kind of loop, we are going to get our new vector, and we call that as a trial vector. So we have our donor vector vng plus 1, and now using this particular operation, we are going to get our trial vector. So let's say we perform these things and we get a trial vector, and let me just randomly give the values to this: 0 1 minus 1 0 2 4 and 1 1 2 and 0 1 3. Actually, the correct way to do this would be, okay, let me do this more correctly. The So I think there is one question also in your this week's assignment, that which one cannot be a trial vector. So this, if I do this incorrectly, probably it can create some kind of confusion. So let me do this a little bit more accurately. So when you are making your trial vector from this x1g plus 1 or xng plus 1, sorry, xng and vng plus 1, your trial vector is going to be like in the first element, the value is going to be either from here or from here. So in this particular case, it is sure shot that the first value is going to be 0. Second values can be minus 1 or 0. So the thing is, the value on this trial vector is going to be either this value, sorry, either the corresponding value from the original vector, or the corresponding value from the donor vector. It cannot be anything else. So let me ask you, Mr. Manohar, what are the two values that are possible for this particular case, for so this is first solution, second solution, third solution, third variable. What are the two values that can be that will be used for placing one value here?
3 or 1.
Yes, correct. So this kind of question is asked in the assignment, so you can use this concept to answer that. So let me also quickly do some random choosing and do that. So we have 0 0 1. Let's say we choose this one, and we have 1 1 2 and 2 1 1 and 2 1 0. So let's say we get our trial vector as this from random, or doing the operation that we have discussed in the previously. Okay. So this we get our trial vector. Now we have, so this was the part of recombination. We have done the recombination. Now we have to do selection. So for selection, we are going to compare our old or our original solution and our recombined solution. So the trial vector, or I think the original solution was called as target vector. So let's call this target vector. So we will compare the value of the solution at each corresponding solution. Solution 1, the value of function at solution 1 will be compared for the uh, trial vector and that for the target vector, and whichever is satisfying the criteria. Let's say we want to minimize, so if this particular value, the solution from the trial vector is it's lesser, then we are going to choose this particular vector. If the solution for the target vector or the previous generation vector is lesser, then we are going to choose that particular vector. So that operation we are going to do, and then we are going to finally get the new generation to do the iteration again and again. So for before this, I think we can do check also, check for termination check before going to the next iteration, whether we have achieved said minimum threshold for convergence or the number of loops we have reached. We can check that, and after, if it is not, then we can get the new generation. So let's say in the new generation, first solution was better in case of, in the trial vector, so we take this, and the second solution was better in case of the previous generation or the target vector, so we take this, and let's say our trial vector was better in third and fourth, so this will be our new generation. And then this will be treated as the initial population for the next iteration, and we do the same operation again and again. So is that clear, Mr. Manohar? The theory is clear.
Yes, sir.
So we will go ahead and do the programming for the differential evolution. Okay, so let me share my screen. So the screen one, okay. So I hope my screen is visible. It is visible, right?
Yes, screen is visible.
Okay. So let me just close my other machine. Okay, yeah. So let's do the differential evolution example that sir has discussed in the class, and let's see if you have any doubt in like how the things are proceeding, then you can stop me and we will discuss. Okay, so let's see. So we have this thing. I will refer to this. I wrote this code. We will refer to this and we'll try to write. So first of all, I think it is clear for you how to, how to install this thing. It is pretty straightforward. Let's not spend much time on that. We will see directly start to code. So we have our function with two variables, and whatever operation we are going to do, we can write inside these curly braces. First in x1 square plus x2 minus 11, and then the square of this thing, and then x1 plus x2 square minus 7, then square of this thing. So this is our function, and then x1 is equal to x2, the like how we decided the domain. So we are going to make the domain here, that is difference by zero point 0.1, and just calculation of value using for the grid. So we need the value for the grid. So x1 and x2 and fn. Then just we can do the contour and we can see how these values are looking. So we have FL, number of levels we can choose. Let's say we choose 50. Control S, Control A, and Control Enter to run this. So we can get the contours like this. Let me change the color to something so that, like sir change it to blue, I will also change it to blue. So when we get the point, we can plot it here. Okay, so this is the uh, part for just the plotting. I think this is pretty straightforward and you must be pretty familiar with this thing. Now we want to do our differential evolution optimization. So let's write the code for that. For that, we need to make a function that takes the variables, sorry, the vector instead of the two variables separately. So we will just modify this one. So x1 will be x of 1 and x2 will be x of 2. So this is our function that we are going to use. This is the objective function, and now we can just simply call the differential evolution optimizer, and you can just put the value of function. First argument is the value of function. Then the second is you can give the lower and upper bound for these variables. So 0 and 5. Sorry, 0 and 0 is the lower bound for x1 and x2, and upper bound is c 5 and 5. So yeah, so let's see what we get using these things. So we have, it has, for by default there was 200 iteration in my case, and it has best estimate of 3 and 2 it has achieved. So let me also see what are all the other estimates. So we'll go to result, dollar member, sorry, member and dollar population. So if we see, so by default what it has done, it has taken 20 solutions in my one generation. So and all the members of these solutions have converged to the value of 3 and 2, which is actually the answer, and we can see that by plotting these things. So points, we can plot all the things or one of the things. Let's plot all the things. Points result dollar member dollar population, and we want to point x1, so which is the first column of this thing. To select the first column, we need this particular index, that is square brackets comma 1. So comma is going to select all the rows for this first column, and then we have to do the same thing for the second column also. Then we can do PCH16 to get a bigger circle, and color we can give it red so that it is more clearly visible. So Control S, Control A, and Control Enter to run the thing. So this is the solution that we are getting, which is actually the correct solution also. What we can do further than this is, we have just here given function lower bound, upper bound. We can, as sir had discussed in the class, we can change some of the control parameters also. So to do that, we just use this function, and then it will automatically show us the control. And NP, as we saw in our hand example, that we chose um, we chose five solutions. No, we chose four solutions in our generation. Let's say if we choose four solutions again here, let's say if it converges or not, and maximum iteration we can change to, let's say, 50 iterations. And f value, that is the weightage when we are doing the mutation, let's take it as 1, and the CR, let's take it as 0.5. So let's see what we get in this particular case. We don't know whether it is going to converge or not. So yeah, so it has not converged. As you can see here, it has not converged. And let's plot the result also to see the variation with iteration. So it is showing that it has converged, but the correct solution, it has not reached to that correct solution yet. Because we have shifted our iteration to 50 and given only 4 populations. So let's see the population members inside this. Let's see what are all the values for that. So you can see it has not converged, but we are able to control the population, sorry, so solution numbers inside the uh, population pool. And if we give, let's say, 10, then I think probably it is going to converge. So yeah, let me just erase this. So then it converges. So, oh, still it has not converged to the actual thing. Okay, let's see what are the values it is going to. It is going to 2.88 and 2.07. So we cannot, I don't think it will converge nicely if we are giving less iterations. What happens if we give 100 iterations? Let us see. So it moved a little bit closer to the solution. Yeah, 2.98 and 2.048. So this, we can play with these things, and you can see that we need certain number of solutions or in the population, and a certain number of iterations to get to the correct solution. So this is just a trial and error process. We have to do for our specified problem, and we have to see which is the appropriate number for this optimization. So is there any doubt in this thing, Mr. Manohar?
No, sir.
Okay. So then what we will do is we will move to MATLAB first. So I'll just minimize this. So this is done. Then we'll move to MATLAB. We'll do some coding. So